Welcome to the second edition, second half of the mole concept, or the mole notes. Okay, so we left off with some practice problems. I hope by now that you have made your best attempt, and if you hit any snags, you would have asked me by now. But of course, it's never too late. So if you're still struggling with any of that, just let me know, okay? So we're moving on to something called percent composition in this unit. And this is something that analytical chemists, such as forensic scientists, use to identify and define unknown substances. Okay, so for example, let's say you just simply wanted to know, and I often use water as our basic example. Let's say I wanted to know what the mass of that molecule is made up by. Just the hydrogen or just the oxygen. How much hydrogen is in a molecule of water? How much oxygen is in that molecule of water? And so if you're a forensic scientist, for example, you could have some unknown substance, and you want to know what percentage of that substance is perhaps a poison or something toxic or some kind of dye or something like that. Okay, so you can find the percentage by mass of each of the elements in a compound. And in your notes, you've already gotten the percent composition formula, which is equal to the grams of the element in 1 mole. Grams of the element, so that's the molar mass, right? Over the molar mass of the whole compound, okay? So how many grams of the single element you're talking about over the entire molar mass times 100? Because it's percent. Percent means times out of 100. So here's an example, and this example is right out of your book. That's why I just copied it and then pasted it into your notes as one big picture, so you don't have to make any changes, but you can and should make notes or highlights. Okay, so sodium hydrogen carbonate. It's also called baking soda. Very complicated name for a very simple substance, or maybe it's not so simple. If you took introductory physical science in 8th grade, one of the very first labs that you did in that class 2 years ago or more was heating baking soda. And when you heated baking soda, you realized that a lot of carbon dioxide came out of that. So it's a very interesting substance. It's also the active ingredient in some antacids for relieving indigestion. So what they want you to do in this question is to determine the percent composition of sodium hydrogen carbonate. In other words, what percent of that molecule is sodium, what percent is hydrogen, what percent is carbon, and what percent is oxygen, for a total of 100%. So number one, you simply determine the molar mass. Molar mass, we've done that many times. You've had lots of practice so far. So you find the molar mass of sodium in that molecule. There's only one. There's only one hydrogen, there's only one carbon, and there's 3 oxygens. So determining the molar mass of each is simple. Adding them all together, you get the total molar mass of sodium hydrogen carbonate to be 84.01 grams per mole. And the second step, and the final step in determining percent composition, is now you use the percent by mass equation that we just saw in our notes. So for sodium, you take sodium's mass over the whole and times it by 100. So 27.37% of the molecule is sodium. Do the same thing for hydrogen, 1.2%. That makes sense because hydrogen's mass is very small. Remember, your answers have to make sense. Carbon, there's only one of those, so you divide that by the whole, and that's 14. And then, of course, what you would have suspected, it's not always this clear, but what you would have suspected, since there's 3 oxygens, oxygen's mass is rather big compared to the other ones, that has the most percentage. And when you do the math, you find out that all of them add up to 100% to check your answer. So here's some practice problems that you're going to work on after the notes are over. So, oops, sorry about that. So you are going to determine what the percent composition of the hydrogens, the phosphorus, and the oxygen in phosphoric acid. And that's the answer, but I'm going to need to see the work on your notes, okay? So don't just give me the answer. And then the same for this question. You're going to have to do this twice and make no assumptions. So which has the larger percent by mass of sulfur? Is it sulfuric acid or that second molecule? The numbers are different. You're going to have to do the math to figure it out, okay? And prove that that's the answer, okay? So that's the answer, but you have to prove to me why. So I want to see your work. Okay, so moving on, we've got two more types of problems we have to figure out here. One is determining the empirical formula for a substance. Now, what is an empirical formula? The empirical formula for a compound is the formula with the smallest whole number mole ratio of the elements. Pretty much everything we've seen so far in this class has been the empirical formula. So here's an example. The empirical formula for hydrogen peroxide is HO. That is the smallest whole number mole ratio of the elements. But there's something else called the molecular formula. And hydrogen peroxide's molecular formula is H2O2. In both formulas, the ratio of oxygen to hydrogen is 1 to 1. And we're going to see why this is important in a moment. Okay. So here's the first example. Also, this example is right out of your textbook. Okay, methyl acetate is a solvent commonly used in some paints, inks, and adhesives. Determine the empirical formula for methyl acetate, which has the following chemical analysis. So someone has done percent composition and found that methyl acetate has 48% carbon, 8% hydrogen, and 43% oxygen. So what you're going to do with those percentages is you're going to convert each of those into moles. How do you do that? You have to make an assumption here, okay? And really, it's the only thing you can do. You have to assume that each of those, out of a 100-gram sample, imagine that you have a 100-gram sample, each of those percentages would be number of grams, right? So for carbon, it's going to be 48.64 grams. For hydrogen, it's going to be 8.16 grams. And for oxygen, it's going to be 43.20 grams. And the only thing you can do with grams, and I taught you this last week, was convert it to moles. You can't convert it to anything else. It's the only thing you can do with grams. So we're going to convert each of these to moles by using the molar mass. So the molar mass of carbon is 12, and so grams cancels out, leaving us with 4 moles of carbon, 8 moles of hydrogen, and 2.7 moles of oxygen. Okay, remember, we're trying to find the empirical formula, chemical formula. So part 2 is to calculate the simplest ratio of those moles by dividing each element's moles by the smallest calculated value. So the smallest calculated value was 2.7. So if you go back here, the smallest calculated value was 2.7. See, these are higher. So divide each of the moles that you got, that one and that one, by that one, and then that one by itself. So 4 for carbon divided by the smallest is going to give us 1.5. So that means there's 1.5 moles of carbon. 8 is going to be, for the hydrogen, is going to be divided by the smallest. That gives us 3 moles of hydrogen. And then 2.7 divided by itself is just 1, so that's going to be 1 mole of oxygen. So the smallest mole ratio is 1.5 to 3 to 1. 1.5 to 3 to 1. Multiply each number in the ratio by the smallest number, in this case 2, that yields a ratio of whole numbers. So you can't have a half, is what they're saying here. So you'd have to multiply each of these by the smallest number that gives you a whole number. So in this case, it's 2. So 2 times 1.5 is 3, 2 times 3 is 6, 2 times 1 is 2. So these are your actual numbers, your subscripts that you're going to use in your empirical formula. And so the answer is C3H6O2. That's the empirical formula for this substance. And that's how you determine empirical formula. So what many students do is when I give them a practice problem, they ignore the previous example. So what you have to do is you're going to simply use this example and go through the steps, one by one, go through the steps exactly like they're shown to determine the answer to this question, okay? So you're going to determine the empirical formula for the compound that contains the percentage of elements at the left. This is the substance picture, but we don't know what it is yet. We know it has aluminum, 35.98%, and it has sulfur, 64.02%, but what's the formula for this substance, okay? And so if you go through those steps of first converting, just assuming that this is a 100-gram sample, this is going to be 35.98 grams of aluminum, and this is going to be 64.02 grams of sulfur. Convert those to moles, and then once you get the smallest number, divide that by the, that'll be your denominator, and then put the other numbers on top, and you will getting your answer, okay? So you're going to work on that later. And then the second one, which I mentioned before when we talked about hydrogen peroxide, is the molecular formula, okay? So in order to, this gives the actual number of atoms of each element in one molecule or formula unit of the substance. So here's an example of why this is necessary. Acetylene gas is a gas used in welding. I'm not sure if any of you are familiar with welding, but if there's different kinds of welding. If this type is very hot gas that has a very high temperature flame, because it's burned. Acetylene gas is burned with oxygen, and when it's burned, it just makes a very hot flame. Okay. So its empirical formula is CH. That's the lowest ratio. But that's the same as benzene, which is a completely different substance. And it can be very confusing. So, because they're very different chemicals, you want to have the molecular formula to differentiate between the two, okay? So, to determine the molecular formula, you must know the molar mass of the substance and then compare that mass with the empirical formula. So you have to know the empirical formula, which we already know, of CH. So the molar mass of acetylene is 20, and you're going to be given this information, don't worry. And of course, we're going to have more practice with this. So the molar mass of acetylene is 26.04 grams per mole. Again, we don't know what the formula is yet, we just know what the molar mass is. When taking the empirical formula of CH, you get 13.02 grams per mole. So if you divide the molar mass of acetylene, which is 26, by the mass of the empirical, you get 2. Real simple. This means that the molar mass of acetylene is 2 times the mass represented by the empirical formula. So the molecular formula must contain twice the number of carbon and hydrogen atoms as represented in the empirical formula. So the answer is 2 times the empirical formula, which is C2H2. So once you determine the empirical formula of something, it's so simple. You just divide, and you get a number, and then you multiply that number by the empirical formula, and you just fill in the blanks. C2H2, okay? So you're going to practice, okay? So a compound was found to contain 49.98 grams of carbon and 10.47 grams of hydrogen. The molar mass of the compound is 58.2 grams per mole. Determine the molecular formula. So just like we did on the previous example, solve for the molecular formula, okay? So go back in your notes and look that up. All right. after the notes are over. The notes aren't much longer. We're going to have plenty of time in class to work on these problems, okay? So what's a hydrate? A hydrate is a compound that has a specific number of water molecules bound to its atoms. An example pictured here is that really pretty crystal called copper 2 sulfate. How do you name them? The compound is written, so you just simply name, we know what copper 2 sulfate is. We can look that up in our periodic table of the ions. We can look up sulfate, and copper 2 we know as a +2 charge, so we can write it out, right? So naming them is relatively simple too. The compound is written followed by a dot. The dot does not mean multiply, like in math. It just means it's like a separator. And then a coefficient that corresponds to the number of water molecules bound to it. So another example is sodium carbonate. Decahydrate. So the deca refers to the 10 coefficient, and the H2O you just call hydrate, okay? So sodium carbonate decahydrate. That's how you say it. So here are the formulas of some hydrates. Again, this is in your notes. I only included part of this in your notes. You didn't need all of these. It's redundant after a while. So, you know, it's just like when naming covalent compounds. You've got mono, di, tri, tetra, penta, hexa, hepta, octa, deca. And for some reason they skipped nona, but it's in there for 9. And so you've got, you know, dihydrate, trihydrate, heptahydrate, octahydrate. Okay? Now, what's really cool is it can affect the way certain gemstones look, these hydrates. Opals, I don't know if you're familiar with any gemstones, but opal, I believe, is a birthstone, for example. The presence of water, the presence of these hydrates in minerals and other impurities gives them their different colors. Okay, so the concentration of the water versus the other minerals gives opals their different colors. And then further changes in color occur when the opals dry out. So opals will change color over time. You see, they're mined out of the ground, and the water concentration is pretty stable there. But once they're pulled out, they will dry out over years, many, many years, and the colors will change over time. That's pretty cool. So how do you determine the formula of the hydrate, of a hydrate? Let's look at this. So calcium chloride hydrate has a mass of 4.72 grams. You've got this sample, okay, and it's you massed it on the scale, and it's 4.72 grams. You heat it up for several minutes over, in a dish over a flame, and you get an anhydrate. That means that it's dry now. Anhydrate just means that it's dried out. And it's found to have a new mass of 3.56 grams. I mean, obviously, you guys are pretty smart. You know what happened. The water was essentially heated away and evaporated away. So the difference between the 4.72 grams initially and the second mass, 3.56 grams, is water. If you just subtracted those, you get the mass of the water. So you're going to use this information to determine the formula of the hydrate, and then you're going to name the hydrate, okay? So here are the steps. Right here, here are the steps. Find the mass of the water driven off. Step 1. You simply subtract, and it's 1.18 grams of water. All right, step 2. Then you convert the mass of the anhydrate, the leftover, to moles. So you take 3.56 grams, and you multiply it by your numerator over denominator, oh my gosh, I can't think of the name, sorry. You know what I'm talking about. Conversion factor. There you go, Mr. Keene, get with it. By the conversion factor, which is 1 mole per 110 or 110.98 grams per mole, but you want grams on the bottom because that's what you want to cancel out, and you want moles. So you just divide that 3.56 by 110.98, and you get 0.032 moles. And then you do the same thing for water. You convert the mass of water also to moles by simply multiplying by the conversion factor of moles over grams. Grams cancel out, getting you 0.655 moles of water. And then you find what's called a mole to mole ratio. And this is new, but we're going to be using this a lot in the future. So you divide each of those numbers. You put water on top always over your anhydrate. You divide them, and it's 2 to 1. Okay? So you essentially get the answer of 2. So it's a 2 to 1 ratio. And so since the compound contains 2 moles of water for every mole of anhydrate, the formula is 2. The coefficient that goes in front of water is 2. So it's calcium chloride dihydrate. Okay? And that's how you find the formula of a hydrate. So you're going to practice this. This is, I believe, our last slide. A hydrate of magnesium sulfate has a mass of 13.52 grams. The sample is heated until no water remains. The magnesium sulfate anhydrate, meaning the water's gone, has a mass of 6.6. Find the formula and name the hydrate. So do the same process on the last slide that we did and determine the formula for that. Okay, so you have the remainder of the period now to work on all of those problems, work with your neighbor, and if you guys can't figure it out, obviously come to me and I will help guide you through it.